Swayam Prabha. Digital India. Educated India.
So, for a steady irrotational flow of non-viscous incompressible fluid, we have already seen the previous equation, and now we are talking about a steady irrotational flow of non-viscous incompressible fluid. All this incompressible, non-viscous, irrotational we have already seen. Now we are telling it's a steady flow. The moment we say steady flow, what will happen to this term dou phi by dou t? Once it is steady, there is no change in time. So if there is no change in time, this term will disappear or it will vanish. It goes to 0. Now what we have is only this, that is P by rho plus V square by 2 plus GH is nothing but constant C. Alright. So now if you look at, this is your pressure divided by rho, is a velocity square by 2 plus GH is nothing but your potential, okay, potential energy. So that is equals to constant. And if you take any 2 points in a flow without considering the losses, this term is going to remain same. Okay, it's going to be constant. Okay, so in other words, we can write down P by rho G plus, I'll take the G just down or divide by G all the places. We can write down P by rho G plus V square by 2G plus H is equals to constant H. So now what is this V square by half 1 by 2 V square by G? It's almost equivalent to, if you look at, half mv square. Okay, so it's a kinetic energy. This is your pressure energy and this is the potential energy. Okay, and that gives rise to your total energy. But here what we are writing is in terms of heads. Okay, so it is nothing but your energy per unit weight. What we are writing is energy per unit weight and we are getting it in terms of head. Okay, so the first term P by rho G is called as pressure head. Second, V square by 2G is called as velocity head, or that's nothing but your kinetic energy per unit weight. Similarly, the potential energy is nothing but your datum head. Okay, so potential energy per unit weight. Okay, and the total, all three together, is going to give you the total head available at a particular point. So as I said, the pressure difference P2 by gamma minus P1 by gamma, let us say there are 2 points 1 and 2, the fluid is moving from point 1 to point 2. Okay, the pressure difference that is P2 by gamma minus P1 by gamma represents the energy spent by the pressure force in moving 1 unit of fluid, 1 unit weight of fluid from point 1 to point 2. Alright, so that is the energy spent, whether it is pressure energy or kinetic energy or potential energy, it is the energy spent for moving 1 unit weight of fluid from one point to another point. Alright, so this is what is Bernoulli's equation, and this equation is very, very important and you can apply that to solve many problems given that the conditions are satisfied, which you should also always keep in mind. Okay, now let us look at some of the applications of this Bernoulli's equation. All right, so application to real fluid flows can also be done, although we have derived this for ideal fluid scenarios or inviscid flows. Based on Euler's equation we have derived this. Still, this Bernoulli's equation can be applied to real fluid flows, assuming that the flow is inviscid, and later we can do some corrections. So basically, because of viscous shear, some energy losses are going to take place. So there will be some loss, and in Bernoulli's equation we have not considered that. Okay, so the energy equation you can modify. Okay, what we have written that, okay, if it moves from one point to other point, we said that the energy is going to remain constant, but no, it is not going to remain constant. If we want to equate, and what we will do, the total energy head or total head at point 1 is equals to total head at point 2 plus some energy loss that has happened over the distance while it is moving. Okay, so now once we write it down, it is important we find out what is that H loss or head loss. So we'll see how do we find out head loss for different types of problems. Okay, so basically head loss cannot be found beforehand. You cannot find out beforehand. You basically assume that okay, there is no head loss or neglect and do the analysis and obtain one approximate solution. Once you obtain the approximate solution, then you modify the results by introducing some kind of coefficients. So maybe in a laboratory condition, you exactly know theoretically what you should have got. With the real fluid, you got some value. So you know the difference or the coefficient that you can find out by taking the ratio. That coefficient can be used for further applications. We'll see a lot of these applications as we move on to the next lectures. But right now, at least we should understand that the Bernoulli's equation can be applied. Okay. So it may be applied without much error for gradually varying unsteady flow. As I said, for steady flow, you can assume and correct it, but this can also be applied for unsteady flow, but for gradually varying. If it is rapidly varying flow, then there is a sudden change and temporarily it is changing quite fast, then it may not be giving you a very good result, but for gradually varying flow, you can still apply without much error. Now for flows of gases where the change in pressure is small fraction of the absolute pressure, the fluid may be treated as incompressible. So we said that this Bernoulli's equation is applicable for incompressible flows. That's why gas is compressible. But in case the compression or compressibility effect is not really much, okay, or with respect to the absolute pressure, if the difference is not really or change is not really much, then we can still consider the fluid as incompressible and apply Bernoulli's equation for that flow. So it depends again from problem to problem, and you have to understand what is really happening and then apply the theories or the concepts, then only it is going to be correct. Just like that, arbitrarily you should not be applying. All right. Okay, now having understood different heads, let us look at some other terminology. So here what I'm trying to explain you are the two terminology. One is total energy line and one is hydraulic gradient line. So if I find out the total energy at this point, I'll take the pressure head plus velocity head plus datum head. All three together is going to give me the total energy. Okay, so all if there is a tank and there is a flow through pipe and there are some changes in the pipe diameters, contraction, expansion and so on, there is going to be some loss all through this path. Okay, as the fluid moves all the way, there will be some losses. So if we technically the head should have been constant from beginning to end, so I should have drawn just a parallel line and come up to this, but because of various losses, there is going to be a drop continuously. Okay, so this loss is going to be taken into account when you calculate. All right, we'll not get into all these things right now. There will be pipe entry loss, friction loss, contraction, expansion, all these losses are there, but the energy at any point, including the pressure head, velocity head and datum head, is going to give you the total energy at that point, and if you join, you will get the total energy line. Now similarly, if I just subtract or I don't consider the velocity head along this, then the line that I could draw is going to be called as hydraulic gradient line. Okay, so the hydraulic gradient line is nothing but your datum head plus the pressure head. Okay, these two are going to give you the hydraulic gradient line. Okay, so we will not discuss more details of this right now, which we will come across as we go on in the course. Okay, now let us quickly look at a typical problem, example problem. Okay, so this is application of Bernoulli's equation again. What I have shown here is a kind of siphon. So if you look at, this is a reservoir and there is a pipe. So you have a tank. So let us say in earlier days, people used to empty some tanks, let us say large, some kerosene drums. People used to use some kind of pipe in the drum and then suck it at the bottom, and then once the flow starts flowing, then they leave it to a dam which is kept at a lower elevation. That's nothing but your siphonic action. So it works very well, and people have been using it frequently. Okay, so let us look at similar kind of problem here, which is shown. So you have a tank here, and there is a pipe which is going like this. It's a theoretical question, so you can see nice profile, but practically it may not be like this. But it's okay. The principle is going to remain same. And there is this pipe top is at this elevation, and then this goes down to an elevation of uh, this much, and finally there is a nozzle. Okay, so the problem statement says like this: the siphon shown in the figure has a nozzle of 150 mm long. So this nozzle that is connected here, this part is 150 mm long. It is attached to the exit end. Okay, the diameter of the nozzle is 150 mm and the diameter of the pipe is 250 mm. The head loss from point 1 to 2. So as the flow moves from this location to this location, there is a head loss, and the head loss from point 1 to 2 is given as 1.5 v square by 2g. Okay, and from point 2 to 3 it is given as 0.8 v square by 2g, and through the nozzle is given as 0.05 vj square by 2g. So where this v and vj are the velocity in pipe and nozzle respectively. Okay, so velocity in pipe is v and velocity through the nozzle is vj. So now the question is asking you to calculate the discharge through this system and the pressure at section 2 as well as at section 3. Now we have to answer what is the pressure at section 2 and section 3. But now the question is, what is the pressure at 1 and 4? Can you tell that? It is all atmospheric pressure, isn't it? So you have the atmospheric pressure at point 1 and 4. Okay, so that's known to you. Now what is the velocity? Velocity at all these points we don't know. But what is the velocity at this section 1? This is a huge tank. So even though there is a water is drawn from that, there is some change which is going to happen. There will be some changes in the motion, but this is going to be very, very less compared to the kind of velocity that is going to exist through the pipe system. So we assume that this is negligible and the velocity at this point is 0. Okay. So with this, let us now try to solve. So how do you solve? You have to apply the Bernoulli's equation at various locations. So which are the locations you can apply? You know the pressure here, you know the pressure here, you know the velocity here, you know the velocity here, you know all the datum or the elevations at all these locations. So it is only one unknown, that is the velocity at this location. So I can quickly take the Bernoulli's equation, apply between section 1 and 4 and get the velocity that is going to exist at this point, and that will give me the discharge. That's the first point that I should target and solve it. Okay, so let me say this point is considered 0 and below that this nozzle end level is negative. Okay, and above this is positive. Now quickly, if we apply the Bernoulli's equation between section 1 and 4, so I can write down the Bernoulli's equation, that is P1 by gamma plus V1 square by 2g plus Z1 is equals to P4 by gamma plus Vj square by 2g plus Z4 equals to plus H head loss. Yes, you have to consider the head loss. Head loss is going to be equal. Okay. Now if we have this expression, let us start substituting. So we know already the P1 is equals to 0, that is atmospheric pressure, and we are talking in terms of gauge pressure. So it is considered 0. V1 is the velocity that I explained. It is very, very negligible, or it is considered 0. P4 is also 0. Pressure at this nozzle exit is atmospheric again, so it is 0. So substituting all these values, we can write down Z1 is equals to Vj square by 2g plus all the head losses, and the datum Z4 is nothing but minus 0.15. So from here it is negative. So now here if you look at, there are two unknowns, V and Vj, and finally you could write down the expression for Vj in terms of V, and G is there, you can always substitute the value. So now here we will apply the continuity equation. Okay, because at these two sections, whatever flow is coming in at the section 1, the same flow is going out, so discharge remains same. So we can write down A1 V1 equals to A4 V4. Okay, so applying the continuity equation between section 2 and 4, you can write down 2 and 4 or 1 and 4, doesn't matter. 1 is basically sometimes get confused, the whole section, but let us say 2 and 4. So the velocity in this pipe is, let us say, V2 or V. So A2 V2 is equals to A4 Vj. So from this relation, we can write down Vj equals to 2.77 V. That's the velocity through the pipe. Okay. So relation between the nozzle and the pipe velocity has been established. Okay. Now once you have done that, you substitute this equation 2 in our previous equation 1 that we got here. Okay. So by substituting that, you can find out what is the value of velocity in the pipe as well as in the nozzle. Okay. So once you get these velocities, then you can find out the discharge. Discharge equals to area into velocity. So you take either the velocity through the pipe and take the corresponding area, or velocity through the nozzle and corresponding area of the nozzle. Don't confuse or don't misplace these two things. Okay, whatever velocity you are taking, the corresponding area you have to take to find out the discharge. So you got the discharge. Now let us find out the pressure. So pressure at P2, if we want to find out, we already know all the parameters at 1. So if we now substitute the Bernoulli equation, we apply the Bernoulli equation between section 1 and 2, we could write down Z1 is equals to P2 by gamma plus V square by 2G plus Z2 plus the head loss that is taking place between 1 and 2. Okay. So once you substitute this, you can find out the pressure at P2 is going to be minus 1.518 meter, and that minus is negative gauge pressure. Negative gauge pressure, as I have already told, it is nothing but your vacuum pressure. So you got a vacuum pressure of 1.518 meter, and this anyone can suck and generate that kind of vacuum pressure and pull the liquid if the pipe is that much high. Now I can keep on raising this pipe elevation, so I have to basically increase the amount of vacuum pressure so that I can pull the liquid. Now I give you this option to find out what is the maximum height we can take this pipe so that we can still pull the liquid. You cannot go beyond absolute zero. The absolute pressure cannot be negative. Vacuum pressure or gauge pressure can be negative, but absolute pressure cannot be negative. So assuming the absolute pressure can be reached up to zero, you find out what is the maximum height that we can have here. Okay, that is for you to find out. Now let us look at the other question, that is what is the pressure at point 3. Apply the equation between point 4 and 3, Bernoulli equation, and again substitute all the values. If you know already the values that Z is 0 here and the pressure is 0 at point 4, and just substitute all the values, you will be able to write down what is the pressure. That is pressure at P3 is going to be 1.308 meter. That's the gauge pressure. All right. So this is how you apply various apply the Bernoulli equation to various problems and try to solve the problem and get a solution or find out the pressure or velocity. And these are basically correlation between the pressure, velocity, and the datum. So all three you can find out through a system or through of a problem through by using the Bernoulli equation. All right. Okay, so with this, I think we'll stop the class here, and thank you so much. Have a good day. Bye bye.